Here we see another one. This is in South Burlington, Vermont. You can see it here. This is the intrusion here. This was the country rock that existed. And right along the margins here, you can see there was there'd be contact metamorphism here. So that's cool. Oh, and this is a little, just throwing this in. So map view versus cross-section. We often do a lot of cross-section stuff in rocks. So just to show, of a Snickers bar, that's a map view looking down from overhead. Okay, that's what it's called. This is called the profile view. This is gigantic Snickers. I couldn't find a good picture. I never saw a Snickers like this. But the point here, other than the Snickers looks awesome, is a profile view means a side view. If you drew profiles in any sort of mapping unit, you know that. This is what we're going to call a cross-sectional view of Snickers, as if you cut down through it. Now, we can take a Snickers, cut down through it. You can see the cross-section. I'm going to show some cross-sections of Earth. And we can't, let's cut down through Earth a mile and a half and see what's there. We can't do that, but we can draw diagrams that represent that, as we did here. So, please, if you have this sheet, please copy this down now. Pause it. Okay, so rock can be metamorphosed by high heat alone. It doesn't have that high pressure. It's not buried very deeply. And that is usually lava or magma cooking it. Not buried deeply, you have lower pressure. And here's a volcano here. In this case, this rock existed. You had magma underground. It probably forced its way through a crack. There's a lot of pressure, so it's really pushing through a crack. Come through, you have a volcano here. This case, it was pushing through a crack. Didn't make it all the way, started going horizontal. This is called the sill, by the way. This is called a dike. And what you see is this symbol here represents that this magma cooked all the rock here that it touches. That's what that represents here, here, and here. So this is a symbol for contact metamorphism. And this is a cross-sectional view of Earth's surface. We have to often, again, we can't see them to sort of project what it would look like if we were to cut down. Again, we cannot cut down to Earth 700 feet just to see this. The key thing I have here is that what you're going to see, this is the rock symbol for sandstone. This is the rock symbol for limestone. And it looks like a brick wall, but it's the limestone. And then when that limestone gets metamorphosed by this lava that went through here, what you're going to have right along the margins here, where it's red, you're going to have marble. Because limestone, when it gets metamorphosed, will become marble. You have partial melting. Sandstone, right here and here, I don't have it marked, here and even here, that becomes quartzite. And that's really where the idea of, think of the quartz sand, the sand of the sandstone, all of the pieces of it kind of melting together, very much like the chocolate chips. That's kind of where that analogy, that comparison comes from. You're thinking of the sand grains all kind of melting together to be one big lump. And quartzite is much harder than sandstone. If you were to try to break it, you hit sandstone with a hammer, it will break. Quartzite, all kind of melted together, much more like one solid mass, much harder to break. I learned that the hard way out in the field once, which is time for another story. So, this is in the notes that you have, and what this chart shows is temperature. I convert it to Fahrenheit and miles. So Fahrenheit, 400, just to give you a sense of 1,500 Fahrenheit, 1,800 Fahrenheit. These are unbelievable temperatures. You and I normally don't experience these kind of temperatures. The really, really kicking fire in a wood stove, like kicking, I think gets in the range of 800 degrees. I've actually asked around. Some people don't actually really know. 800 degrees about, and that's just like kicking. So this is unbelievable temperatures. And these are depths below our surface in miles, 3 miles, 6 miles, 9 miles, 12 miles, 15, 18 miles of depth. Okay, so this is pretty unbelievable. That's some of these rocks that you see. This rock that, I have right here, the slate off my neighbor's roof, formed at a depth of, 5, 6 miles below the surface. It's pretty crazy. So this is sort of the sedimentary zone. I think I did color this in. The yellow represents sedimentary zone. So this is the burial of any sort of sediments, compacted, cemented, will form sedimentary rock. But once you start getting down below this level, and maybe that's 4 miles, 4.5 miles, this is getting a metamorphic zone where you start having those minerals hot enough pressure for those minerals to start changing partial melting, recrystallizing, minerals or clays changing to mica, and then you start having slate. And when slate is buried deeper, it's getting hotter, deeper down. It will transform into phyllite. It'll slowly transform into phyllite and schist. And the rock gneiss forms in this range here, according to this, between 15 and 18 miles of depth and 1,100 degrees Fahrenheit or 1,000 degrees Fahrenheit, which again is unbelievable conditions. If you see over here, I often ask students in my class, well, what do you think this is? Why are these lines here? Think about that just for a second. Okay, this is like not labeled or anything because what happens here, this is total melting. Okay, it's much hotter, and then there's this weird thing with pressure too, and how the pressure affects melting point. Won't get into that, but this is where whatever that rock is totally melted, it becomes magma. It will, at some point, cool, solidify, and become an igneous rock. So now we're out of the sedimentary and metamorphic zone. This is the igneous zone, magma zone. One thing I like to think about, tell kids, well, so you have gneiss and it forms 15 miles deep or more, which is pretty amazing. 15 miles of rock on top of it, 15 miles below your feet. And that's where that forms. It doesn't form at lower depths. How do we then get pieces of gneiss around? How do I have some here in class? How do you can find them out and about? You find them a lot in the Northeast, find it in Vermont, New York. It's not uncommon. It's around. How does it get from this depth to be on the surface? And you can find it in a lot of places. Think about that. Okay, this is just another picture sort of showing another cross-section of Earth that we often will show. This is a granite intrusion here, so it has the contact metamorphism drawn in there. It has, you're going to see limestone here, you're going to have marble here, because limestone, because metamorphosed becomes marble. You have a vesicular basalt lava flow that flew over this layer of shale. It metamorphosed it there. So just know the contact metamorphism symbol, better the cross-section idea. You know, it's hand-drawn. It helps us understand it's never as cool as the real world. Okay, how do you tell the rock types? Again, where we want to go is in your life, walking along, rocks get picked up. At the very least, can you tell is it igneous, sedimentary, or metamorphic? So, just to review a bit. Igneous rocks have inter-grown crystals that are angular and randomly placed. They can be, if it's glassy, it's igneous. If it's vesicular, it's igneous. If it has fossils, it's definitely not igneous. Okay, it's definitely not igneous. These are some crude diagrams trying to show. This is show under a microscope angular interlocking minerals. This is kind of weird. Sedimentary rocks tend to have, if you can see pieces of rock or sediment, pieces of shells, if it has anything rounded fragments cemented together, any sort of cement visible as opposed to interlocking crystals, or if it has fossils. If it has a fossil, it's definitely sedimentary. Most sedimentary rocks you see will not have fossils because you may be holding a piece that something just coincidentally did not happen to die and fall into that piece. So most sedimentary rocks do not have fossils, but if it does have a fossil, it's definitely a sedimentary rock. This is pretty good under a microscope. A sedimentary rock is going to be like, this would be like sandstone. Rounded sand grains, and then the black is the cement in between. And that's what it would look like. That's what it would look like. I actually have a good, let me just try to pull this up here. This right here, if I can pull this up. This is under a microscope. You know, as I mentioned, you grind that rock down so it is less than paper thin. You can see through it. It's a skill to get it that thin. But this is what sandstone would look like. The sand grains in this case are very rounded, and the green is the cement. I believe in this case the cement, they actually able to dye it green so that it stood out. But so this is the cement and this is the sand grains. Pretty cool to look at some sandstone under such high magnification. So that's very cool. I don't think I have. No, that's much more difficult to tell, so I'm not going to do that. That's that. And then metamorphic rocks, what we have here, metamorphic rocks are going to be composed of crystals. Sometimes it can be fine or coarse. The crystals are in some sort of pattern, layering. It's either going to be foliation, like something like slate, similar, same color, or banding is the different color, or foliation is visible. You won't have fossils generally. And under a microscope, you can see them like this, that this is the pressure was like this, so they all kind of align perpendicular to it. And you often have this high percentage of mica content. It will give it a silvery sheen or have flaky mica crystals to it that are kind of shiny. All this stuff is the skill. You're not going to learn this, the real details here, by me talking and looking at pictures on the board. But it's good information for when you get them in your hands to be able to understand them and really know what to look for.